We have gone through the first two forms of definitions of concave convex functions and the quasi-concave and convex versions of them. Now the next one is when we have a real valued function of a real variable, which is concave, and when we take any point A, take this point A f of A, and draw the tangent line, then the graph stays below the tangent line. Now this, of course, requires the notion of a derivative in the general case as well. So this will be about derivatives of concave and convex functions. Now let us first consider this one-dimensional case, and let us write what it means that the graph stays below the tangent line. Well, for that, of course, we need to have the function differentiable at this point. Now, here we have a non-empty subset U of R, U convex, open, A in U, and F on U to R, a real valued function, and we assume that F is differentiable at A. Now, let us first write the equation representing the tangent line. Now, this point here, that's A, f of A. Let us take any point here, x, y, this point x, y on the tangent line. And we know that the slope of the tangent line is f prime of A. So, well, that means and well, this y, okay, that's then y minus f of A divided by x minus A when x is different than A. This will be equal to the derivative of f at A, right? Well, so we can solve this for y. Y, that will be f prime of A times x minus A, then plus f of A. Now, what we require is that this y actually, for this to be above the graph, y should be larger than or equal to f of x. So this should be larger than or equal to f of x. Well, we can rewrite this. That is f of x minus f of A. That will be less than or equal to f prime A, x minus A. But now, if we rewrite this part in terms of the generalized derivative, This is nothing but the derivative of f at a. This is the derivative function. This evaluated at x minus a. So the question is whether concavity and this condition, this inequality, whether they are also equivalent in the general case. But it turns out to be so. So that yields our first theorem. Here we'll take let U as a non-empty, open, convex subset of, say, Rp. Now we take it open so that every point will be an interior point, and we can consider differentiability of f at each point in U. F on U to R, a function, now let us first consider the situation at a point A. Assume that A is in the domain and f is differentiable at A. Now this will yield the following results. Now, 1, if f is concave, then we will have this inequality. Then, for all x in U, we will have f of x minus f of a less than or equal to f prime of a. This in the general form, df of a at x minus a. But similarly, if f is convex, well, then minus f will be concave, and we'll have, for all x in U, f of x minus f of a, this time larger than or equal to df of a evaluated at x minus a. Now the strict versions, if f is strictly concave, then we expect to have this first inequality in the strict sense, but of course if x and a are equal to each other, this becomes 0. This becomes this linear map evaluated at 0, there will be equality. So we expect that for all x, this times in U minus a taken out, we'll have f of x minus f of a, that's strictly less than the f of a at x minus a. And finally, we will have the strictly convex version. This will be strictly convex. Well, then we'll have for all x again in U minus singleton a, such that f of x minus f of a is larger than dfa at x minus a. Now here we have these inequalities as a consequence of the function being concave, convex, or the strict versions of that. Now, but what about the converse? Well, as for the converse, it is difficult to say something about the entirety of the function, convexity, concavity, and the strict versions. They do not apply to pointwise evaluation of the function, but they describe the overall behavior of the function on its domain. So just considering what happens at one point, well, that seems to be impossible to yield a converse of this. So we will now consider a situation where f is differentiable on the entire domain U, and well, something similar to this. We will check whether that will be equivalent to the concavity, convexity, and so on. So the second part of this theorem is, now assume that f is differentiable on U. Now, f is concave if and only if for all x1, x2 in U, well, we have this inequality here. This first inequality, this time x1, x2 replacing xn f of a. That is f of x2 minus f of x1. That's supposed to be the derivative of f at x1 evaluated as x2 minus x1. Similarly, f is convex if and only if for all this is this time larger than or equal to this. F will be strictly concave. F is strictly concave if and only if. Now, for all x1, x2 in U, again, we wish this to hold in the strict sense, but if x1 and x2 are equal to each other, this will be dfx1 at 0. Its value will be 0. This will be 0 as well. Thus, we'll have equality there. But this time, if x1 is different than x2, then that implies that f of x2 minus f of x1 is less than the f of x1, x2 minus x1. And finally, f is strictly convex, if and only if for all x1, x2 in U. If this holds, then we'll have this, but the inequality will be in the reverse direction. Of course, the proof for concavity, well, that will yield the proof for convexity because minus the negative of a convex function will be concave, and that is, and well, for the strict versions is similar, so we will prove the concave version in both cases and leave the proof of the remaining versions as an exercise. Proof 1. Now let's start by assuming that f is concave. Now we wish to show that then this inequality holds. Okay? Well, so far we have made an extensive use of the derivative being equal to the directional derivative of f at a in the direction of x minus a. Now, no matter what x I take, since u is open and a is a point in u, well, all the vectors, including x minus a for any x in u, they will point into a, and since f is differentiable at a, all such directional derivatives, they will be well defined. So, let x be in u and t in 0, 1. To find the directional derivative, we need to form the directional derivative at a in the direction of x minus a. We need to form f of a plus t times x minus a. Well, subtract from that f of a, divide that by t, and well, its limit as t tends to 0, that will exist because we know that f is differentiable at a. Okay? Now, well, this is superfluous. We have 1 over here. Now, if we consider a plus t times x minus a, well, this minus a divided by t, the limit of that as t tends to 0. But what do we know? We know that f is concave. Now here, let me rewrite this. This will be equal to f of 1 minus t times a plus t times x. Thus, this argument here is a convex combination of a and t. By concavity, this will be larger than or equal to 1 minus t f of a plus t f of x, since f is concave. But then I can form here f of a plus t times x minus a. I can take this f a to this part. Well, this will be larger than or equal to t times f of x minus f of a. But I can also, since t is in 0, 1, I can also take this as 1 over t. Since t is different than 0, I can divide by that. Moreover, it's positive, so the sense of the inequality will not be changed. Okay, but now, since f is differentiable at a, f sub x minus a at a exists. Since x minus a also points into cap u at a, but since u is open, every vector points into that. So, well, I can take the limit of this, the limit of 1 over t f of a plus t x minus a. This, minus f of a. Now this limit as t tends to 0, that will be exists and will be equal to f of x minus a at a. Moreover, if I take the limit of this, well, since for all t in here, we have this inequality and this part does not depend upon t. It's constant with respect to t. This will be larger than or equal to f of x minus f of a, and this will be equal to d f of a at x minus a, establishing the desired inequality. So the formula that we discovered to hold for the one-dimensional case, that carries over to the general case. Okay? But this is just one-sided, that is, concave implies this inequality. Well, here, for the other versions, that's, as I said, the other versions are similar. And here we utilized the coincidence of the derivative at a point, evaluated at a point, well, with the directional derivative in the direction of that point. Now then, let's come to 2 and do it for f, but we already have half of that. If f is concave, then this holds, just, well, take x2 as x and x1 as a in part A. We already know that for all x1, x2, f of x2 minus f of x1 is less than or equal to df of x1, x2 minus x1 by part 1. Now let us do the converse. Conversely, assume that for all x1, x2 in U, f of x2 minus f of x1 is less than or equal to df of x1, x2 minus x1. Now we are supposed to show that f is concave. Now to do that, let's take any 2 points, x1, x2, and any t in 0, 1. And then try to show that f of tx1 plus 1 minus tx2, that's larger than or equal to tf of x1 plus 1 minus tf of x2. So take any x1, x2 in U and t in 0, 1. Now, to shorten notation, set x naught equal to tx1 plus 1 minus tx2. We're supposed to show that f of x naught is larger than or equal to t f of x1 plus 1 minus t f of x2. Now we will use this. Now here, let's consider the following trick. Well, in several proofs, you add to a quantity a particular zero in a particular form, so that you will have equality. That thing plus zero, they're equal to each other. Or we multiply something by 1 in a particular form. Well, the value stays invariant, but that yields some result. Now here, we'll consider the following particular zero. Let me distribute this x naught over here as follows. Then t x1 minus x naught plus 1 minus t x2 minus x naught. Well, this will be 0, because this is just this quantity minus x naught, but I have written that as tx naught plus 1 minus tx naught. This will be equal to 0. So, f of x naught will be equal to f of x naught plus 0. But now what we know is df at x naught, well, this holds for any x1, x2, df at x naught, well, that's a linear map. When it's evaluated at 0, it yields the value 0. So let me then add to this df at x naught times this particular 0, t x1 minus x naught plus 1 minus t x2 minus x naught. This is 0. So the value of this, that's 0 as well. So this is just equal to f of x naught plus 0. But now, we can, well, by linearity of df of x naught, this is equal to f of x naught plus t times df of x naught. This is just a symbol for a linear map at x1 minus x0, and then plus 1 minus t times df at x naught x2 minus x0. But I can apply the hypothesis to this now. x1 and x2, this is x1. Well, here, this plays the role of x1 in here, and this plays the role of x2. So this will be actually less than or equal to, no, this is larger than or equal to f of x1 minus f of x naught by hypothesis. And this will be larger than or equal to f of x2 minus f of x naught by hypothesis. So, since t and 1 minus t, they are non-negative, so, well, multiplying by them, and multiplying this by t and that by 1 minus t, that does not change the inequality. So this will be larger than or equal to f of x naught plus t times f of x1 minus f of x naught plus 1 minus t times f of x2 minus f of x naught. But what's this? Now here you have minus t f of x naught plus 1 minus t f of x naught, and so these cancel each other, and you just get t times f of x1 plus 1 minus t times f of x2. But this was f of tx1 plus 1 minus tx2. Thus, we conclude that f is concave. Thus, f is concave. Again, the rest is similar. That's left to you. So that completes this. So that takes care of the third kind of characterization. The first one, just a secant line stays below the graph, no matter the secant connects whatever 2 points on the graph. Well, we took that as the definition of concavity convexity. The next was, well, the epigraph and subgraph. Well, the subgraph should be convex in the product space if the function is to be concave. For convex functions, the epigraph should be convex. That was equivalent. Now, this is the counterpart of, well, if the function is differentiable at each point on the graph, if you draw the tangent line, the graph of the function stays below the tangent line. Now, next is, we have two more left. Now, one is, well, the slope of a concave function, which is a real valued function of a real variable, which is differentiable, then the slope is non-increasing. And that's equivalent to concavity of a differentiable function in the one-dimensional case. Okay, now let's deal with that problem as well. But as we also have noted before, well, here in calculus, if you have a real valued function of a real variable which is differentiable, then the derivative is a real valued function as well. So we can compare f prime x with f prime y as real quantities. One will be less than or equal to the other. But now here, in the general case, what is to be compared is, well, linear maps. You have a linear map, then another linear map from Rp to R. Well, what does it mean? That one is larger than or equal to the other. But we'll use the same trick here, as we did in here, as we did in generalizing the derivative to vector-valued functions of several variables. Now, we will write the condition in the one-dimensional case, then rewrite that in such a way that it also makes sense in the multidimensional case, and then check whether that works. Now, so let's first consider the one-dimensional case. Now let U be a non-empty subset of R. Let this be open and convex. Assume that F is differentiable on U. Now let us first write what it means for f prime. The derivative of this, in the calculus sense, is non-increasing, which will correspond to concavity. Now, f prime is non-increasing on U, if and only if, for all x1, x2 in U, x1 less than or equal to x2 implies that f prime x1 is larger than or equal to f prime x2. Of course, if x2 is less than or equal to x1, then the reverse inequality will be implied. Well, this if and only if. Now, if I do not wish to keep track of whether x1 is less than or equal to x2 or x2 is less than or equal to x1, I can rewrite this in the following form. For all x1, x2 in U, now let me consider f prime x1 minus f prime. Let me write it in the reverse order. No, here, that's better. F prime x1 minus f prime x2, x1 minus x2. Now, if x1 is less than or equal to x2, this will be non-positive, but this will be non-negative, so the product will be less than or equal to 0. If x1 is larger than or equal to x2, this will be non-negative, but in that case, well, this will be non-positive because it's non-increasing, so the inequality will be reversed. But in either case, this will be less than or equal to 0. And if this is less than or equal to 0 for all x1, x2 in U, this follows. So these two expressions are equivalent to each other. But what's the advantage of this? Now here, this is f prime x1 times x1 minus x2. And here, this is f minus f prime x2 at x1 minus x2. What do we know about this? If we wish to translate this to general terms of derivative, this is nothing but df x1 is evaluated at x1 minus x2, and this is just df at x2, x1 minus x2. But I can use, okay, so this if and only if, in the one-dimensional case still, x1, x2 in U, and I can write it by using the addition between functions, this at x1 minus x2 being less than or equal to 0. This is exactly this expression, but now written in more modern terms rather than in calculus terms, in terms of the derivative we have defined. Okay, so this makes full sense. Well, also when f is a function defined on a subset of Rp. So let us adopt this as the definition of the derivative of a real-valued function of p variables to be non-increasing, and for the remaining three cases similarly. Well, we do not know, but let's check whether that works in translating. Well, here, the derivative being non-increasing, that's equivalent to concavity. Okay? Let's do that. on u to r, a function. Assume that f is differentiable on u. Now we say that the derivative of f on is, now we have, well, let's start with non-increasing. We started there. Is non-increasing. If for all xy in u, we have dfx minus dfy evaluated at x minus y is less than or equal to 0. Next, we will say it's non-decreasing. Well, if all this holds, but this time larger than or equal to 0. Next, decreasing. That's the strict version of non-increasing. If for all xy in u, well, again, if x and y are the same, well, then these two functions will coincide. This will be 0, and you'll get 0 equal to 0. So to have strict inequality, we have to postulate that x is different than y. That should imply that dfx minus dfy, that at x minus y should be this. Finally, increasing. And this, of course, for each of them on u. Well, this time, if we have this different, then this implies this time larger than 0. Now the question is whether we will have the derivative of a differentiable function like this being increasing, well, non-increasing, whether that's equivalent to concavity. And likewise, this to convexity, this to strict concavity, and this to strict convexity, and it will turn out to be so. Now here, and also in what we have done before, now we assume to know facts about the one-dimensional case as given to us from calculus. But if you have doubts about that, well, go and check the one-dimensional case. Well, in any calculus book, I would say, but some calculus books do not mention convexity and concavity, some real analysis. For example, in Bartle, well, there is just the notion convex that's just once, that just occurs once in the entire book, and that in a footnote or something like that. Okay, but we'll take that is, what we'll do here is, we will actually well, take this. The derivative of f is non-increasing on u, that being equivalent to concave. We will actually reduce that, well, when a real valued function of a real variable, which is differentiable, that's concave if and only if f prime is non-decreasing. But to prove that is easy. You can do that on your own as well. To prove the theorem here, we need some famous and important formula from differentiation. We introduced the notion of a derivative, but, well, the derivative that was linear, so the derivative of sums and the derivative of scalar products, and that followed automatically from that. But in calculus, if you introduce differentiation, what's sort of one of the most important and widely used differentiation rules, it's the so-called chain rule to differentiate the composition of two functions. Now here we'll have the counterpart of that, and we will need it. Okay, now let A be a non-empty subset of Rp, B a non-empty subset of some Rq, F on A to B a function, and G on B to some Euclidean space, a function again. Now let's assume that A is an interior point of A. Let's call f of A B. That will be in B, but we assume that it's in B interior. Now the question is, when f is differentiable at A and G is differentiable at f of A B, will then the composite function G circle f be differentiable at A? Well, the answer is yes. And if f is differentiable at A and G is differentiable at B equal to f of A, then the function G circle f on A to R is differentiable at A, and in fact the G circle at A is just the derivative of G at B composed with the derivative of at A, where B is f of A. You just compose the derivatives. This is on RQ to RR. This is on RP to RQ. So this takes it from RP to RQ, and this from RQ to RR. Now, well, we will omit the proof of this, but you can check it from Bartle if you wish. But we will use it. Now, our theorem. Okay, so that'll say that non-decreasing derivative, that will be equivalent to convexity, non-increasing to concavity, and the rest. But let's first have a break and then continue next hour.